These are the notes for section 5D on average atomic mass. An average atomic mass is this number that you see right here on the periodic table. It's found in the bottom of each box on the periodic table. It's also referred to as the atomic mass or the atomic weight of that particular element. This page talks about the definition of average atomic mass and how we calculate it. The average atomic mass is the weighted average of the individual masses of the isotopes of an element. So you could put the word individual here. But it's a weighted average, and it's weighted according to the naturally occurring abundances of the isotopes of the elements. Most of the elements on the periodic table have at least a couple of different isotopes, and so this number just tells us on average how much one of those isotopes weighs, but it takes into account how often each isotope appears. So if a particular isotope is found much more abundantly than the other isotopes, it'll have a greater effect on the average mass. Before I talk to you about how that mass is actually calculated, I want to talk to you about a unit called the atomic mass unit. Around the 1950s, physicists and chemists around the world decided that they would take a standard atom and compare all the other masses of the other elements according to this particular atom. And the atom they chose, for a variety of different reasons, was carbon-12. It's a specific isotope of carbon that has 6 protons and 6 neutrons, and they gave it a designated mass of exactly 12 atomic mass units, or 12 AMUs. Oops, sorry about that. So what's an AMU? Well, an AMU is exactly 1/12 the mass of an atom of carbon-12. So imagine this little black dot right here is an atom of carbon-12. So it's got 6 protons and 6 neutrons in it. If you took that atom and you chopped it up into 12 even pieces, each one of those pieces would weigh 1 atomic mass unit. It's a very, very, very small mass. It's equivalent to 1.66 times 10 to the negative 24th grams. But that's what an atomic mass unit is. And so when you see average atomic mass, it's in units of atomic mass units, which are just very, very tiny units of mass. Here is a table at the bottom of your notes that just gives you a summary of different properties of subatomic particles, so I just want to fill this in for you. Remember that an electron has a charge of -1, a proton has a charge of +1, and a neutron doesn't have a charge at all. The second column shows you the masses in atomic mass units of an electron, a proton, and a neutron. Notice that the proton and the neutron have almost the same mass, but a neutron's a little bit heavier. For our purposes, we're going to say that a proton and a neutron weigh about 1 AMU each, so I'll put a 1 there in both of those parentheses. An electron is very light compared to the other two, so it contributes virtually no mass to the atom, so we're just going to put a 0 in there, even though it does have a very small mass. The column on the very far right shows you the mass in grams of each one of those particles. You don't have to memorize that information, I just think it's useful to notice how light they are. So this next page, this will be page 29, gives you a definition for how we calculate average atomic mass. What we do is we take the relative abundance of each isotope and multiply it by its corresponding mass, and then we add all of those products together to get an average atomic mass. So I'll show you how to do that in the next slide. Here's a problem that you might see. You're given a particular element, and it was put through a mass spectrometer, which has given you information about each isotope, how much it weighs, and how abundant that particular isotope is. And our job is to find the average atomic mass for this particular isotope. So what you do is you write down the mass of the first isotope, 11.0092, and you multiply that by its percent abundance. But divide by 100 first, so that percent is written as a decimal. So this will be 80.09 becomes 0.8009. And when you multiply those two together, you get 8.8173. Do the same thing with the next isotope. It weighs 10.0129 atomic mass units. We're going to multiply it by its relative abundance, which is simply its percent abundance written as a decimal. And we get 1.9936. Then you simply add those two numbers together. I'm going to round to 4 significant digits because each of my percent abundances only has 4 significant digits. And that is my average atomic mass. If you look on the periodic table, you'll see that the element with that mass is boron, 10.81. So truly, the first isotope in this case had a greater bearing on the overall mass of the isotope because we found it 80% of the time. So notice here we're not taking a straight average, but we're taking a weighted average. I'm going to go through the problem at the bottom of the page as well. In this particular problem, we have more isotopes. Notice as I read the problem, I'm going to fill in some values below. Chromium has 4 isotopes. Chromium-50 has a mass of 49.946 atomic mass units and a relative abundance of 0.0435. So this problem was a little nice because I don't even have to take my percentages and divide by 100. That's already been done for me. So when I multiply those two together, I get 2.1727. Chromium-52 has a mass of 51.941 and a relative abundance of 0.838. So I'll put that in this second line, and when I multiply those together, I get 43.5266. Chromium-53 has a mass of 52.941 and a relative abundance of 0.0950. Multiplying those two together, I get 5.029. And the last isotope has a mass of 53.939, but I am not given a relative abundance. It's useful to remember that if these had been percent abundances, all the percentages would add to 100. Since they're relative abundances, all of these values right here should add to the number 1. So if I'm missing one of them, I simply take 1, I subtract 0.0435, then I subtract 0.838, then I subtract 0.0950, I end up with 0.0235. So that is the relative abundance of this last isotope. When I multiply the mass by the relative abundance, I get 1.2676. So to get my average atomic mass, I need to add those 4 values together, and I get a mass of 52.0 atomic mass units. So I'm just going to round that to 3 significant digits because my masses were my fewest numbers of significant digits at 3. So hopefully between these problems you can get started on page 30 and 31. You want to complete all those problems and show your work for those problem sets. Good luck, and talk to me in class if you have any questions.
Made with Doodlecast Pro.